Welcome to the Insightful Professor. Today we'll be discussing semantic enhancements to the entity relationship model. Recall that back in the 1970s, Chen developed the entity relationship model. This was revolutionary for database design. However, it was only the beginning in research to produce better semantic models. As we shall see in our video today, some points related to the application domain are subtle. However, they are important and must be reflected in the model and subsequently within the database. Remember that the purpose of the model is to develop effectively a blueprint from which the database can then be built. This blueprint must reveal or disclose such subtleties if they are to be incorporated into the database. Our goal is to produce a semantically rich model from which we then can produce an accurate database which reflects all of the semantics in the application domain. Extensions to the entity relationship model were proposed by Chen as well as other researchers. We'll be addressing a few of these in this video. The goal of these extensions is to accurately represent semantics of the application domain within the model. In this video, we will discuss some of these enhancements. Weak or dependent entities, cardinality constraints on relationships, concept of existence dependency, generalization and specialization of entity types, sometimes referred to as an ISA relationship. The primary reference for the material that we'll be presenting comes from a paper that was presented by some researchers at the University of Michigan. Let's begin by discussing weak entities. Within the context of an application domain, we are likely to encounter many entity types. Some of these entity types directly contribute to the application domain. That is, these entities exist in their own right. These are referred to as strong or independent entities. There are also entity types that we might encounter that are included within the model, but their presence is based upon their association with a strong entity type. These are referred to as weak or dependent entities. It's the relationship between the weak entity and the strong entity that give the weak entity its identification and hence justification for being included within the model. Strong entities and weak entities are represented a little different within our entity relationship diagram. The strong or independent entity type is drawn using a rectangle, while the weak or dependent entity type is drawn using a double-bordered rectangle. Let's look at an example where we have a one-to-one relationship between student and car. So a student is enrolled at the school and drives a car. It is while that student is enrolled at the school that information about the car is of interest to us. If the student is no longer enrolled and leaves the school, we no longer have any interest in information about that student's car. So when information about the student is removed from the database, so too will the information about the car driven by that student. Thus, it's the association of the student, the strong entity type, with the car, the weak entity type, that makes the information about the car meaningful or relevant to us. Looking ahead to our relational database implementation of this part of a model, we would have these entities becoming tables. There would be a foreign key And the idea would be that if we delete a row from the student table, there would be a cascading delete, removing the row from the car table that identifies the car for the student we just removed. Another important concept is what we refer to as a cardinality constraint. A cardinality constraint specifies the number of instances of an entity type that can or must be associated with each instance of another entity type within a relationship. Here we're showing a relationship between department and employee. Such a relationship might indicate a cardinality of 1 for a department and a cardinality of many for employee. Question that we have, though, is there an upper limit to the value of m, to the many? How many employees can be assigned to a department? Is there a lower limit to m? How many employees must be assigned to a department? So given a relationship between employees and departments that we refer to here as assigned to, we've described this as a one-to-many. An employee is assigned to one department and a department has many employees assigned. However, suppose there's a business rule that imposes a restriction on the number of employees that could be assigned to a department. This diagram, as shown here, does not even suggest that possibility. What we're looking for is some way of incorporating within the diagram a method or some mechanism for showing this business rule or suggesting that there is an upper limit or a lower limit on the cardinality. So the maximum cardinality could be recorded solely in the documentation of the data model, which we refer to as the data dictionary, but not incorporated within the diagram. Ideally, what we would like to do is have that maximum cardinality reflected in the diagram. We want this picture to express more information if possible, and that's what we'll now take a look at. We're talking about maximum here, but note that we could also specify a minimum cardinality for an entity type. Here's one way to do it. Using the crow's foot notation, we again are indicating one-to-many, but we could actually add a little bit more information to clarify the point of the many. We could say the many will range from 1 to 10. There would be a minimum of 1 and a maximum of 10. So no more than 10 employees could be assigned to a department, rather than simply saying many and leave it open-ended. We also could modify the way that we express this upper limit and lower limit by using a notation that I've seen some diagrams, LB for lower bound, which would be our minimum, and UB for upper bound, which would be our maximum. Here, there is no absolute standard convention for expressing this idea, but it is important to recognize that different diagramming techniques have suggested that this is important and provide some means by which we could express this cardinality constraint. So it is an important semantic notion that we would like to capture within the diagram. The idea of a minimum cardinality raises another issue: whether every instance of an entity type must participate in the relationship. We have already provided some explanation of existence dependency. Let's now say that existence dependency describes whether an entity in a relationship is optional or mandatory. For example, the business rules of an application domain might dictate that an address might be associated with a person. Such an association indicates a mandatory existence dependency for the relationship between the person and the address entities. An example of an optional existence dependency can be a business rule that states a person might or might not have dependent children. Let's reconsider department and employee, and we ask a couple questions. Can there exist a department which does not have any employees? Can there exist an employee who is not assigned to some department? Note that neither of the questions may be clearly answered from our diagram. Is there always at least one entity instance, or could there be zero? We need some way to distinguish between an always situation and a sometimes situation. Thus, we wish to include more semantic information in our diagram, reducing the need to consult the data dictionary to understand the application domain. Let's consider a business rule such that every employee must be assigned to some existing department. Furthermore, a department might not have any employees assigned to it. Thus, this optionality can be indicated using a bounded notation, such as we presented already, expressing both a lower bound, a minimum cardinality, and an upper bound, a maximum cardinality. Tiori, Yang, and Fry used a notation where there was a circle positioned near the cardinality of the entity type to indicate optional participation. A solid line near the cardinality indicates mandatory participation, or a minimum cardinality of 1. Although these two notations differ in diagramming methods, it's important that we have some means by which we can indicate optional and mandatory participation of entity instances within a relationship. The importance of being able to express these subtle semantics becomes more significant when we transform the conceptual model to a relational model, that is, to a set of tables. Such semantics dictate things like the delete rules for foreign keys. Another important semantic issue is the notion of generalization and specialization. If you're familiar with object-oriented programming, you know this concept by the term inheritance. Here we're referring to it as an is-a relationship. It's a special relationship that occurs in almost all application domains. A motor vehicle can exist in many forms. Each form has some attributes common to all vehicles. Each form might also have attributes unique to that form. The commonality gives rise to the generalization. Every vehicle is going to have a vehicle identification number. Every vehicle will have a make. Every vehicle will have a model, regardless of whether that vehicle is a car, a truck, a motorcycle. So here we note that a vehicle is the general case, and car, truck, and motorcycle would be the specialized case. Another set of terms would be the vehicle is the supertype, car, truck, and motorcycle are subtypes. A car is a vehicle. It's a type of vehicle. A truck is a vehicle. And finally, a motorcycle is a vehicle. So the terminology says that the car is a subtype. And of course, as we mentioned, truck and motorcycle likewise are subtypes. Additionally, a vehicle is the supertype. Note that a car, or a truck, or a motorcycle might each have some attribute or attributes that are unique to that particular type of vehicle. So they're not shared by all vehicles. Those attributes would be associated specifically with the subtype. For example, a car might have an attribute such as number of passengers. This will not apply to, say, a commercial truck. A commercial truck might have attributes such as gross weight, number of axles, and these attributes would not apply to a car, nor would they apply to a motorcycle. So the supertype then represents the common attributes. This is the notion of the generalization, and the subtype would be the specialization, revealing attributes or properties that are unique to that particular type of object. As we look at generalization and specialization a little more closely, we can distinguish between what is called a disjoint is a relationship and a non-disjoint. A disjoint is a relationship has each occurrence of one subtype being identified only as that subtype. That is, if the vehicle is a car, it could not also be a truck. It could not also be a motorcycle. It must fall into one of those categories. We say that a car is not a motorcycle. How do we represent this in a diagram? We would see something along this line. The is-a relationship is drawn as an oval connecting the supertype and the respective subtypes. The notion of disjointness is indicated by the letter D within that oval. And this would tell us that if you have a vehicle, it is a car or a truck or a motorcycle, but it cannot be any combination of these. This is indicating non-overlapping subtypes. There are other diagramming methods that use a distinctive notation to convey this notion. For example, you might see, instead of this oval, you might see this little semicircle. The open semicircle would suggest non-disjoint or potentially overlapping. And the semicircle, which has the X through it, would indicate that it is disjoint. Each vehicle must be one of these subtypes. The specific details of the diagramming notation are not as important as recognizing the concept of what's being presented here and the importance of that. Let's take a look at non-disjoint. In a non-disjoint is a relationship, an entity occurrence could be classified as more than one subtype. For example, if we find in our application domain that we have athletes, and we say, well, an athlete could be a golfer, an athlete could be a tennis player. Is it possible that an athlete could be both a golfer and a tennis player? If that's the case, our disjoint is a relationship would not allow the athlete to be both. But here, by noting non-disjoint, again using our notation with the N within the is a relationship, we say the athlete could be a golfer, a tennis player, or both. In what is referred to as a covering is a relationship, the supertype covers the subtypes if every occurrence of a supertype is classified as a subtype. So if we have only motor vehicles of car, truck, and motorcycle, then with those three subtypes and a supertype of vehicle, we're able to represent every type of vehicle. But if we recognize that there are other types of motor vehicles, such as, say, a recreational vehicle or a boat, then what we see is we've only allowed for car, truck, and motorcycle. So what we might like to do is, rather than enumerate every single possibility, we'll come up with the idea of having kind of a catch-all or some type of other entity subtype. Consider the example with athlete. We said an athlete could be a golfer or a tennis player or both, but are there other things that would qualify as an athlete? So some athletes could be swimmers, some athletes could be soccer players, But if we're not interested in specifically distinguishing all of the subtypes, then we would have this more generic subtype of other, and we would achieve our covering is our relationship. When we talk about generalization and specialization, we've been suggesting that the supertype will have all common attributes, and each of the subtypes would have those attributes which represent specialization. But it's possible that this generalization hierarchy, this is a relationship, can be used to capture semantics in terms of relationships. So in the following example, a subtype participates in a relationship. For example, we say that not every employee has the authority to authorize a purchase order. In order to authorize a purchase order, you must be an employee, but more precisely, you must be an officer within the company. So only officer employees have the authorization to authorize a purchase order. So notice that we capture the relationship with this subtype and some other entity type. If we had made the association between employee and purchase order, that would imply that any employee has the ability to authorize a purchase order. We could clarify that point within the data dictionary, but notice that we're able to show that notation here, that restriction, within this diagram without the need to consult the data dictionary for clarification on the authorize relationship. Notice also that here we're using Tiori-Yang and Fry's notation for optional participation. So a purchase order must be authorized by one officer, but an officer need not authorize a purchase order. Having seen how subtypes and supertypes can enhance the semantics of an entity relationship model, we now consider when it might be most appropriate to use this representation. To do this, we'll consider a situation where a company has three types of employees: hourly employees, salaried employees, and contract consultants. All employees are identified through a badge number. They also have a name, address, and a date of hire. Hourly employees have an hourly rate of pay, while salaried employees receive an annual salary and have a stock option. Contract consultants have a billing rate and an associated contract number. When we develop the data model, we have three choices to consider from this scenario. We could define a single employee entity type. The advantage to this would be it's conceptually simple. The disadvantage would be that the entity contains all attributes for three types of employees. Some of these attributes would be optional attributes. Hence, within the database, these attributes, or many of these attributes, would contain null values because they don't apply. The second choice is to define a separate entity type for each of the three entities. The disadvantage to this is that it does not recognize the common properties of employees, and users would need to be careful in selecting the correct entity type. The third choice would be to define an employee supertype with hourly, salaried, and consultant subtypes. The advantage of this approach would be that it recognizes the common properties of all employees while also recognizing the distinct properties of each subtype. The designer must consider each situation when deciding on the use of subtypes and supertypes. In general, we identify the following conditions as indicators of when to consider the use of subtypes and supertypes. First, there are attributes that apply to some, but not all, of the instances of an entity type. Second, the instances of a subtype participate in a relationship unique to that subtype. In this video, we presented extensions to the entity relationship model. These extensions provide the ability to more accurately represent semantics of the application domain within the model. The enhancements we discussed were weak or dependent entities, cardinality constraints on relationships, the concept of existence dependency, and finally, generalization and specialization of entity types, which we referred to as an ISA relationship. As we've shown in our examples, the use of cardinality, optionality, and generalization can enhance the semantics of the data model. Although there's no agreement on the graphics of an entity relationship diagram, the various approaches do recognize the importance of these enhancements by providing some graphic mechanism to represent them. If you found this video informative, give us a thumbs up. Furthermore, consider subscribing to the channel to be notified when future videos are posted. And once again, thanks for watching.